Hi there, welcome to lecture 7 of Fox, Recursion. Very powerful, very dangerous. Okay, and what I'm showing here on the screen is an example of the data that lies within recursion. So, I was the subject of a demo, okay, as an instructor of an online class. Let's say, what if I wanted to see the view of the student? So I can launch this tool that shows me the view of the student, and boom, crash, boom, 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 boom. The whole system crashed with this beautiful infinite sort of, pattern that got produced. And there was no resurrecting the computer. You just had to do a hard reboot, pull out the plug, put it back in. Okay. I'll show you how this actually came about a little bit later. But before that, let's recap from last time. Okay, last time we were talking about induction. In particular, various forms of induction. Strengthening the induction hypothesis, leaping induction, and we use that to easily prove that postage can be done. Strong induction, that's the default induction that you should, if in doubt, default to. Because when you're proving the induction step, it allows you to assume more, P of 1 up to P of n. Okay? And get practice, get practice, get practice. There's no other way to become good at induction. Practice, practice, practice. All various kinds of problems, lots of problems in the book, pop quizzes, exercises, just practice, practice, practice. Tinker, 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 practice, practice, practice. Okay, we talked about strategic games, so you see induction is everywhere. Greedy algorithms, recursion, which we're going to talk about today, dynamic programming, strategic games, all the representation theorems, and so on and so forth. It's everywhere. Okay, what are we going to do today? We're going to talk about recursion in particular. We're going to first start simple with recursive functions. Okay, and then we're going to move to the recursive definition of sets, and we'll finally be able to give you a formal definition of the natural numbers without using dot, dot, dot. Okay. And then we'll talk about recursive structures and a level even above that, and where we'll talk about rooted binary trees. Okay, so let me show you how that nice, beautiful, nested windows was created for me in the demo of a commercial tool, by the way, not something that was put together by a 4-year-old. This is a professional commercial tool, so that just shows you how dangerous recursion is. Anybody can get into a mess up. Okay. So, what does the tool do? The tool allows the lecturer to see the screen of a remote student. Okay, so let's imagine a very simple professor's screen. So my screen is this square, is this black square, and inside my screen is this blue, blue square. Okay, I'm just demonstrating something very similar. So what does the student see? So the student sees the professor's screen. So on the right is the student's screen with the blue square that, because they're watching the professor's screen. Now comes the interesting part where the professor launches the tool to see the student's screen. So the tool is going to pop up as, some kind of a window in the professor's screen, and it's going to show the student's screen. So here it is. Okay, so I've launched the tool now, and what's the box? The black box that's inside my screen? Well, that's the window that's showing the commercial tool. Okay? And what's it showing? It's showing the student's screen, and the student is, sure enough, seeing a blue square. Okay, but wait a minute. Now the professor's screen has changed. Okay, so the student's screen needs to update to what the professor's screen is now showing. But wait a minute, now the student's screen has changed. So the professor's screen has to update to what the student's screen is now showing. But wait a minute, and so this process continues. The student screen shows the professor's screen. Okay, and the professor's screen has to update to show the new student's screen, and then goes and the student's screen updates, professor's screen updates, boom! So you see the similarity. I've managed to recreate in this very simple example that crash. Okay. So essentially what's going on here is some form of self-reference. My screen shows what my screen showed. It's kind of like a little bit circular. Why is it what my screen shows? Because what my screen shows, what the student sees, which is what my screen showed. So my screen shows what my screen showed. Wow, I can't even say that without getting into all flummox. Okay, so today we're going to study recursion, and we are going to move to the board. Let's talk about recursion. Okay, so recursion, in a word, self-reference. And self-reference looks bad, it looks circular, so it looks like not a good thing, but it is a very good thing. It is a very powerful thing, but it is a very dangerous thing, self-reference, circular behavior, and so that's why we need to do it well, when we're programming. Okay, and that's why when you program a recursion, it's very, very, very very important to prove that your program works. Because if it doesn't work, provably so, then bam, you get that crash, that, that system that allows me to look at someone who's watching my screen and for no reason wipes out my nuclear meltdown. Okay, so we've used recursion in real life. Let's talk about looking up the definition of a word in a dictionary. So look up word. Well, we all know how to do it. You get the dictionary, and read definition. No problem. Okay. The problem arises is when, as you're reading the definition, you're reading along, boom, you come to a word, that you don't understand. Okay. You don't know the meaning of that word. And so then this method for looking up the definition of a word is not quite complete, because what if you come to a word that you don't understand? And so if you come to a word that you don't know, what do? Well, you just look it up. Look up. Let's call this word that you don't know, X. Then look up X. And now we have a complete definition. But except still there might be a problem. So we're looking up the definition of a complex word, and we come to a whole bunch of words we don't know. The first word that we don't know, we try to look it up. Oh, and when we're looking that word up, we find other words that we don't know. So we look it up. And this could go on forever. What stops it from going on forever is that we have some very, very basic words at the end over here, which, we all know, we take for granted. Okay? And as long as everything can be defined in those basic words, this definition of look up a word, even though it looks circular, because I'm telling you how to look up a word, okay, but I'm using look up in the definition of how to look up a word. So it looks circular, but it will end as long as we have those basic words. Okay, let's get more mathematical and define a simple recursive function. Okay, so let's assume that n is a non-negative integer, so we'll write that as n is in the integers that are greater or equal to 0. Okay, just to specify the domain, and let's define this function f of n, which is equal to 2n minus 1 plus f of n minus 1. Okay. And we ask ourselves, is this a well-defined function? Well, the nice thing is that that you can just program this function on your computer. So, your favorite programming language, on your favorite operating system, go and write a function f, okay? And this is the definition of the function f. And now, where's the self-reference? Where's the circularity? Okay? In telling you how to compute f of n, okay, there's some baby algebraic operation that you need to do, and we all know how to do that, especially on computers. Okay, plus, I'm going to ask you now to compute f of n minus 1, and there's the circularity. To compute f, you need to already be able to compute f. Okay. Now, if we think about it, it's not that circular because, let's, instead of thinking of this as I'm defining the function f, instead I'm defining the function f of n. So this is an object, fn. Okay. And I'm saying fn is some baby algebraic operation plus fn minus 1. This is a different object. It's not totally circular, but it is somewhat circular because I'm defining the function f in terms of the function f. So let's go ahead, implement this in a program, and let's go ahead and compute f of 2. Okay, so f of 2, what happens? Well, it says, I would like to, this 2n plus 1, well, that's 3. Okay, plus I need f of 1. And at this point, your program, which is being executed, says, I have to put this computation on hold and go and search for this guy. So when I put this computation on hold, what technically happens is, you put it on hold. That means that you put it on the stack. You have to save the state. You have to save what you're doing. Hold on stack. What's the stack? It's a piece of memory. Think of it as a block of memory. Okay, and at the bottom of it, there's nothing, and you dump your current state onto the bottom there. So the program, if it ever has to come back to that state, knows where it was. It has to remember where it was, and then it goes about wandering around trying to figure out what's f of 1. So it asks, I need to now compute f of 1. Well, we know how to do that. We've defined this function. It's it's an executable function. That's 2n plus 1, where n is 1, so that's 1 plus f of 0. Now I need to figure out what's f of 0.
Okay, and so I need to put this on hold while I do that. Okay, so on hold, on stack. No problem, while I wander around trying to figure out what's f of 0. So f of 0 equals, no problem, I plug in 0 here, -1 plus f of -1. Okay, put it on hold, because I need to now compute f of -1, so hold. Okay, and I need to compute f of -1. And we all know what's going to happen here. This process never ends. It means I'm going to compute f of 1. I'm going to need f of -2. So go on hold, onto the stack, go for f of -2. It's going to need f of -3. Sooner or later, I'm putting stuff on the stack, Each of these things that I put on the stack uses up a little bit of memory. But sooner or later, no matter how big your stack, it's finite. And so sooner or later, you fill up the stack. And the next time you try to put something on hold, it says, you've overflowed my stack. Stack overflow error. Now, if you have a good, operating system, okay, or a good programming language, it's going to just say stack overflow error, crash, and stop. Okay. But if it's a bad programming language on a bad operating system, this program will just keep on trying to put stuff on hold, and it needs more and more memory, so it takes memory from wherever it can, eats up all the memory that your system has, and eventually your operating system no longer has access to memory because it's all in this stack that's storing the state of this computation. The operating system crashes, you can't move your mouse, bam, nuclear meltdown, unplug, replug. Okay, on, off, that's the solution at that point. Okay, so this is why this is bad. Okay, and we all know what the fix is. The fix is that you have to add a base case. So this, for example, is perfectly fine if n is greater than or equal to 1. Okay, and for n equals to 0, we have to have a base case. So we add 0. So this says that the function f of n, okay, is not totally defined in this circular way. There are some values of n for which I explicitly tell you the value of f. Those values of n for which you don't need to use this rule, those values of n are called the base cases. Okay? So these are what are called base cases. So in this case, base case. Okay, tells you what to do when n equals 0. Explicitly, you don't need to use this rule. But if n is bigger than or equal to 1, then you use this rule, and this rule tells you how to compute f in terms of itself. So this is called the recursive case. Okay. And, I want to point out two things. If you don't have the base case, bam, disaster. But even if you do have the base case, you could get into a disastrous situation. For example, if I had here f of n plus 1, okay, then what's happening is that when you get into the recursive case, you're moving away from the base case. So you're never going closer and closer to values of the input for which I have explicitly defined the output. And so that's also going to be a disaster. So it's important that you not only have a base case, but when you need to use the recursive case, this rule that defines f in terms of itself, okay, so you're trying to compute f of n, and you're computing in terms of f of something else. This something else must be getting you closer to the base case. Otherwise, it's never going to end. Okay, so the recursive case, has to make what we call, recursive progress is important. That means that when you compute f of n in terms of f of something else, that something else must be getting closer to the base case. Okay. All right. So here is an example of a well-defined recursive function. So let me box it. So we'll work with this guy for a while. Okay. And the first question that we might ask is, well, how do we know that it is a well-defined, recursive function? For example, how do I know that I have enough base cases? Do I know that this situation will not occur no matter what n I put as input? So last example, we saw that f of 2, resulted in a bad situation. Okay. And now we see that f of 2, that computation, doesn't end in a bad situation because now, when I call f of 2, it asks for f of 1. When I call f of 1, it asks for f of 0. And now with the base case, f of 0 doesn't need to ask for any more f of anything. It just returns 0 immediately, okay, because that's the case n equals 0. Okay, that's the base case. That's why we need the base case, to stop this process at some point. Okay, and so what happens is we return 0. Okay, what that does is it pulls off the stack and says, oh, this is where I was and I needed f of 0 and you just gave it to me. Okay, so now I can compute this guy, which is 1, so I return 1. Okay, and oh, thank you very much. I can pull off the stack and remember why I needed this guy in the first place was to add it to 3. So 3 plus 1, I now can return 4, which is the answer, and I'm done. Okay, so that's the value of the base case. But how do I know that if I did f of 7 million, it would indeed not stack overflow and it would, come and give me the answer? It wouldn't go off into this infinite chain of stack overflow. Okay. Do I have enough base cases, for example? Okay. And so, in order to see whether a recursive function is well defined, okay, you can rely on what we have already discussed for induction. Okay. So there's a very tight link between recursion and induction. Okay. So remember, I told you induction, even though we're done with our lectures on induction, it's going to be with us for a long time. So let me show you that tight link.